Hello friends, welcome back to my YouTube channel. This would be 41st part of my discussion on distillation, and in this I will continue my discussion on the Lewis-Sorel method. In my previous video on this topic, I have discussed the steps that are involved in the Lewis-Sorel method, and if you have watched that video, you must be knowing that the Lewis-Sorel method is used to find the number of ideal stages in a typical fractionating column. So after discussing the steps in the method, today I will use the method to solve one numerical. In other words, I will be discussing a numerical that is based on the Lewis-Sorel method. So at the end of this discussion, you will be able to find the number of ideal or theoretical or equilibrium stages in a typical tray column by using the Lewis-Sorel method. To begin with, we are going to look at the numerical statement. So you have a feed containing 40 mole percent benzene and 60 mole percent toluene is to be distilled in a fractionating column to get a top product containing 90 mole percent benzene and a bottom product containing 10 mole percent of benzene. A reflux ratio of 3 kilomole to 1 kilomole top product is to be used. Assuming that the feed entering the column is at its bubble point, find the number of theoretical plates required and locate the feed plate by using the Lewis-Sorel method. The VA vapor liquid equilibrium data is provided to us. So you have different values of X and Y which are in equilibrium with each other. So in this case, you have a feed solution. The feed solution is containing 40 mole percent of benzene and 60 mole percent of toluene. And it is to be distilled in a fractionating column to get a top product or the distillate that is containing 90 mole percent benzene in it. And at the same time, a bottom product containing 10 mole percent of benzene is to be obtained. For this, a reflux ratio of 3 kilomole to 1 kilomole top product, that is L0 by D is 3 is to 1, 3 kilomole to 1 kilomole top product is to be used. Assuming that the feed enters the column is at its bubble point, or assuming that the feed enters the column at its bubble point, find the number of theoretical plates or equilibrium plates, or you can say ideal plates required to bring about the desired change. And we are also supposed to locate the feed plate, and for this we will be using the Lewis-Sorel method. What is provided to us? The VLE data, vapor liquid equilibrium data, is provided to you. That means in this case, while applying the Lewis-Sorel method, we will have to use the distribution data. There is no equilibrium relationship as the value of relative volatility is not given. Instead of that, they have given the VLE data, and we are going to use that VLE data. So we are going to use this VLE data to plot the distribution diagram, and then the distribution diagram will be used in the solution. So first of all, let us collect the given information, the given data. The components involved, there are two components. You have benzene and then you have toluene. Which one is the more volatile component? The more volatile component. How it is decided? Since the major component in the distillate is benzene, therefore it is the more volatile component. Because this benzene being more volatile, it will be vaporized to a greater extent, and the distillate therefore will be containing benzene as the major component. So you can decide based on this, or if the boiling points are known to you, you can easily tell the component whose boiling point is less will be the more volatile component. And in this case, benzene has a lower boiling point. Okay, so the more volatile component, how we have decided over here, since the major component in the distillate is benzene, hence it is the more volatile component. Then what information is given regarding the feed? It is a solution of benzene and toluene. We are going to call benzene as A and toluene as B, because benzene is the more volatile component, and I have been using notation A to represent the more volatile component. The feed is a saturated solution. That means once you know it is a saturated solution, value of Q is 1, although we don't need Q in the Lewis-Sorel method. Then composition of the feed is provided to us. The feed is containing 40 mole percent of A. That means the remaining 60 mole percent will be of B. So what is the use of this? XF therefore is 0.4. 40 divided by 100, that is 0.4. So XF is 0.4. Then what information is given for the distillate? The composition is given. The distillate is containing 90% mole of A and 10% mole of B. That means XD is 90 by 100, that is 0.9. Mole fraction of A in the distillate is 0.9. Then for the bottom product, the composition is given. The bottom product is containing 10% mole of A and 90% mole of B. That means XW is 0.1. That is 10 divided by 100. Apart from this, you have the reflux ratio. The reflux ratio, we denote that by R. So R is given to be 3. And then what are we supposed to find? We are supposed to find the number of theoretical or ideal or equilibrium stages that are required to bring about this separation. So this is the given information. And along with this, we also have the BLE data, which we are going to use to plot the distribution diagram. So let us start the solution. First step is we are going to find D and W for a basis of F is equal to 100 kilomole per hour. If you must have noticed, they have not given the feed rate. Only compositions are known to us. So in that case, you can start with a suitable basis. And the most suitable basis is 100 kilomole per hour. So for a basis of 100 kilomole per hour, for a basis of feed to be 100 kilomole per hour, we are going to find out the molar flow rate of distillate and the molar flow rate of the bottom product. So for that, we are going to use the steady state total material balance, which is F is equal to D plus W. So F is 100 basis. So 100 is equal to D plus W. I am calling this as equation 1. Then we will be using steady state material balance for A, that is the more volatile component. So it is F into XF, that is equal to D into XT plus W into XW. So XF is 0.4. Then XD is 0.9 and XW is 0.1. And F of course is 100. So we are going to use this. So therefore you have 100 into 0.4 is equal to D into 0.9 plus W into 0.1. That is 40 is equal to 0.9 D plus 0.1 W, because 100 into 0.4 is 40. I'll just rearrange it. So it will be 0.9 D plus 0.1 W is equal to 40. I'm calling it as equation 2. So if you look at equation 1 and 2, you have two unknowns, D and W. You have two equations. And then you can solve these two equations simultaneously to get the unknown quantities, which in this case are D and W. So for this, from equation 1, I am going to use a value of W. From equation 1, W is 100 minus D. So W is equal to 100 minus D. So I am going to use it in equation 2. So if I do it, this will be 0.9 into D plus 0.1 into W, and in place of W, I am using 100 minus D, that is equal to 40. Therefore, 0.9 D plus 0.1 into 100 is 10 minus 0.1 D, that is equal to 40. 0.9 D minus 0.1 D is 0.8 D, and this 10 after going to the other side, it will be 40 minus 10, that is 0.8 D is equal to 30, that is D is equal to 30 by 0.8, that is D comes out to be 37.5 kilomole per hour. Now we will use this D to get W by this equation. So since W is 100 minus D, therefore W will be 100 minus 37.5, which gives us W as 62.5 kilomole per hour. So in this way, for a basis of 100 kilomole per hour, we have obtained D as 37.5 kilomole per hour and W as 62.5 kilomole per hour. Okay, so after getting D and W, now let us do the calculations for the rectifying section. For that, we are going to use the operating line. Equation for the operating line is yn plus 1 is equal to r upon r plus 1 into xn plus xd upon r plus 1. R is given to us, it is 3. xd is also given to us, it is 0.9. So we are going to use these values in the equation, and you get yn plus 1 is equal to 3 upon 3 plus 1 into xn plus 0.9 divided by 3 plus 1. We have used the values of r and xd. So therefore, yn plus 1 comes out to be yn plus 1 is equal to 0.75 xn plus 0.225. So we have got an equation of this form where yn plus 1 is a function of xn. Now this equation will be used for doing the calculations for the rectifying section. And we are going to start with the first stage. So for the first stage, if you remember in my previous video, I have proved this, y1 is equal to xt. You please watch that video. I'm giving link to that video in the description section. So for the first stage, we are going to start with y1, which is equal to xd. And that is xd is 0.9. That means y1 is equal to 0.9. Now, after you have got y1, or after you know y1 for the first stage, we are supposed to get x1. And for that, we are going to use the distribution diagram. In this case, since BLE data is provided, first we will be plotting the distribution diagram. So on the x-axis, we will be plotting all x values that are provided to us. And then on the y-axis, we are going to plot y. And then the diagonal line is drawn for reference. And when you plot the given BLE data, you are going to get the equilibrium curve. So in this way, now the distribution diagram is ready with us. So we are going to start with y1 is equal to 0.9. We are going to locate that on the distribution diagram. So y1 is located over here. And then after locating y1, I'll be going to the equilibrium curve and getting the corresponding value of x1, which comes out to be 0.78. So here x1 is 0.78. So this is the first stage. Let me write. So this is the first stage I'll write. Or just a minute. I will write over here, first stage. Okay, now we have got, or we have done calculations for the first stage. So this is the first stage. Now let us do for the second stage. For that, again, we are going to use the equation of the operating line. Yn plus 1 is equal to 0.75 xn plus 0.225, the equation that we got previously. For the second stage, this equation will be transformed to this form. y2 is equal to 0.75 x1 plus 0.225. And here, x1, the value that we obtained previously, we are going to use that. x1 is 0.78. So if I use it, I'll be getting y2 as y2 is equal to 0.75 into 0.78 plus 0.225, which gives me y2 as 0.81. Now next we'll have to move on to the distribution diagram, locate y2 and get the corresponding x2. So y2 will be located over here. Then I'll be going to the equilibrium curve and getting the corresponding value for x2. So x2 comes out to be 0.6 3. So in this way, the calculations for second stage are over. So this is second stage. Now we will be doing calculations for the third stage. So if the equation of the operating line, when it is written for the third stage, it will be y3 is equal to 0.75 x2 plus 0.225, and x2 we have obtained in the previous step and we are going to use that value. So y3 will be equal to 0.75 into 0.63 plus 0.225. That gives me y3 as 0.70. So with this value of y3, I'm coming back to the distribution diagram. I'm locating y3 at 0.7, going to the equilibrium curve and getting the corresponding value of x3, which in this case is 0.49. So x3 is 0.49. So in this way, we complete the calculations for the third stage. Okay, so let us move ahead. Then still now we have got completed calculations for stage 1, stage 2 and stage 3. Now let us do for the fourth stage. For fourth stage, the equation for the operating line will be y4 is equal to 0.75 into x3 plus 0.225. And x3 was obtained in the previous step, it is 0.49. I'm going to use that. So y4 is equal to 0.75 into 0.49 plus 0.225, which gives me y4 as 0.59. So I'm going back to the distribution diagram, locating this y4 and getting the corresponding value of x4, which comes out to be 0.38. So x4 comes out to be 0.375. And in this way, we complete the calculations for fourth stage. So if you look at the value of x4, you must have noticed that x4 has now become less than xf, which is 0.4. So x4 is 0.375, which is less than xf, which is 0.4. So the conclusion is the fourth plate is the feed plate. That means on the fourth plate, we have reached the fourth plate where composition is less than xf for the first time. So as x was decreasing, it happened on the fourth stage. What happened? The composition became less than xl. So the conclusion is fourth plate is the feed plate. So I'm going to identify that as the feed plate. So stages in the rectifying section, you have first stage, second stage and the third stage. So this stage is stage number 1, stage number 2, stage number 3. These are in the rectifying section. I hope you are understanding the steps. If you have any doubts, you please mention that in the comment section. Then let us move ahead. So let me first write all those things. So this is first stage, second stage, third stage. This is fourth stage, and we have found that fourth stage is the feed plate, and first three stages, they are in the rectifying section. First three stages, they are in the rectifying section. So now after the feed plate, we will now not be using the equation of the operating line for rectifying section. We will have to use equation for the operating line of the stripping section. So the stripping section operating line equation is ym plus 1 is equal to L bar m upon L bar m minus W into xm minus W upon L bar m minus W into xw. So in this case, feed is a saturated liquid. So if I have to show that this is the feed plate, and when the feed is entering saturated liquid, that means the feed is entirely liquid, and as soon as it enters the column on the feed plate, it is going to move to the stripping section. So as soon as it enters the column, it is moving to the stripping section. Then the reflux stream that is coming from the top, it will be joining this liquid stream, the feed in the stripping section. So the combination of this two, F plus L0, will be L bar. Then the vapor phase that is coming from the stripping section to the feed plate, it will have the molar flow rate of G bar, and when it leaves the feed plate and enters the rectifying section, the molar flow rate will be G. G and G bar are same in this case for when the feed is saturated liquid, but L bar and L. So in the stripping section, in the rectifying section, liquid flow rate is L. And since we have used the assumption of equimolar overflow, L0 is equal to L1 is equal to L2 is equal to Ln. So that means in the rectifying section, on every plate, the liquid flow rate is the same. And same is the case in the stripping section. In the stripping section as well, the liquid flow rate is same for every plate, but its value is different. That means in the case of the rectifying section, in general, if we denote the liquid flow by L, in the stripping section, it will be L bar. I am using bar to indicate that L and L bar are different. Liquid flow in the rectifying section is different than the liquid flow in the stripping section. So I hope this is clear to you. Same is the case with the vapor phase. You have vapor flow rate is same for the rectifying section, and it is same for the stripping section. But in this case, when the feed is saturated liquid, G will be equal to G bar. So if in general you are denoting vapor flow in the rectifying section by G and vapor flow in the stripping section by G bar, for this case, when the feed is saturated vapor, G is equal to G bar. So I have discussed about the types of the feed and what happens when every type of the feed enters on the feed plate. So you please watch that video. So in this case, when the feed is a saturated liquid solution, you get L bar will be L0 plus F. So L bar is addition of the feed which is saturated liquid and the reflux stream. And with this assumption of equimolar overflow, in the equation of the operating line, we are going to replace L bar M by L bar, because L bar is equal to L bar M is equal to L bar M plus 1 equimolar overflow. So I'll do that in the. So the operating line equation now will be written like this: Ym plus 1 is equal to L bar upon L bar minus W into Xm minus W upon L bar M, L bar minus W into XW. You must have noticed I have replaced L bar M with L bar. So L bar is L0 plus F. The reflux ratio, first we'll have to get L0. For that we are going to use the equation for reflux ratio. Reflux ratio is L0 by D. That is L0 is equal to R into D. So R is known to us, it is 3, and D we have calculated, it is 37.5 kilomole per hour for the basis of 100 kilomole per hour, feed to be 100 kilomole per hour. So that means L0 will be equal to 3 into 37.5. That gives us L0 as 112.5 kilomole per hour. So once you get let us get L bar. So L0 is 112.5 kilomole per hour. We obtained previously. F is 100 kilomole per hour. That gives us L bar as 112 plus 100, 112.5 plus 100, which is L bar is 212.5 kilomole per hour. Now W is 62.5 kilomole per hour. We obtained it along with D. So now we will use all these values in the equation for the operating line. XW is 0.1. Again, this is given to us. So that gives us Ym plus 1 as 212.5 divided by 212.5 minus 62.5 into xm minus 62.5 divided by 212.5 minus 62.5 into 0.1. That gives us ym plus 1 is equal to 1.42 xm minus 0.042. So this is the equation of this form. Ym plus 1 is a function of xm for the stripping section, and now we are going to use this equation in our calculations for the stripping section. Okay, so let us do the calculation for the stripping section. Before that, let me write what we have obtained so far. This is the first stage, this is the second stage, this is the third stage, this is the fourth stage. Fourth stage is the feed plate, and stage number 1, stage number 2, stage number 3. These stages are in the rectifying section. These stages are in the rectifying section. Let us move ahead. Equation for the stripping section line is ym plus 1 is equal to 1.42 xm minus 0.42. Now we are going to move on to the fifth stage. For fifth stage, the equation will now be y5 is equal to 1.42 into x4 minus 0.42, and x4 was previously obtained. x4 is 0.375. Let us use it. That gives us y5 is equal to 1.42 into 0.375 minus 0.042. That gives y5 as 0.49. Now I am going to move on to the distribution diagram, locate y5 and get the corresponding value of x5, which comes out to be 0.28. So x5 comes out to be 0.28. So this will be the fifth stage. Then sixth stage, y6 is equal to 1.42 x5 minus 0.042. x5 is 0.28. So y6 is equal to 1.42 into 0.28 minus 0.042. That is y6 is 0.36. So with this value of y6, I'm going back to the distribution diagram. I'm locating y6. I'm going to the equilibrium curve and getting the corresponding value of x6, which comes out to be 0.19. So this is the sixth stage. Okay, so we still till xw x value of x is greater than xw. We are going to do till x becomes less than xw. xw is 0.1. So let us move ahead. So let me first write. So this is first stage, this is second stage, this is third stage, this is fourth stage. Fourth stage is the feed plate. First three stages are in the rectifying section. So these are in the rectifying section. And then we have now moved into the stripping section. This is fifth stage. This is sixth stage. So now let us check for the seventh stage. For seventh stage, the equation will be y7 is equal to 1.42 into x6 minus 0.042. x4, x6 we obtained as 0.19. We obtained it in the previous step. So therefore y7 is equal to 1.42 into 0.19 minus 0.042. That gives us y7 as 0.23. Then I'm going to go to the distribution diagram, locate 0.23, go to the equilibrium curve, and that gives me x7 as 0.11. So x7 is 0.11. So that is the seventh stage. Then let us go for the eighth stage. For eighth stage, the equation of the operating line for a stripping section is y8 is equal to 1.42 into x7 minus 0.042. That is y8 is equal to 1.42, x7 is 0.11. So 1.42 into 0.11 minus 0.042. That gives me y8 as 0.11. And then I'll move on to the distribution diagram, locate y8 and find corresponding x8. x8 comes out to be 0.05. So this happens in the eighth stage. And you must have noticed now x has become less than xw, which is equal to 0.1. This suggests that we have reached the reboiler. and our calculations for stripping section, they are completed. Okay, so let me first write what we have obtained so far. So this is first stage, this is second stage, this is third stage, this is fourth stage. Fourth stage is the feed plate, and then you have fifth stage, sixth stage, seventh stage, and eighth stage. Eighth stage is the reboiler. And first three stages, 1, 2, and 3, they are in the rectifying section, and then the other stages, stage number 5, 6, and 7, they are in the stripping section. So in this way, we finally get the number of ideal stages in the tray column, in this particular tray column, by using the Lewis-Sorel method. So X set is 0.05, which is less than XW. That means the 8th stage is the reboiler that I told you. Stages in the stripping section, these are 5th, 6th, and 7th stages. 5th, 6th, and 7th. The number of theoretical stages are 7 plus 1 reboiler. Number of stages in the rectifying section are 3, 1, 2, and 3. Number of stages in the stripping section are 3, 5, 6, and 7. And feed plate is the fourth stage, or fourth plate is the feed plate. So in this way, you have to use the Lewis-Sorel method for finding number of ideal stages in a typical tray column. So I hope you have understood the steps. I have simplified as much as possible. If you have any doubt, you please mention them in the comment section. And I'll come back to you with the solution for your doubts. For now, thanks for watching my video. Do subscribe to my channel and tell your friends to subscribe to it, and be with me in the coming videos where I'll be discussing various aspects of chemical engineering. Very soon I'll be starting my discussion on liquid extraction. For now, have a nice day, and I'm sure you'll join me in my next video on another topic in chemical engineering and in mass transfer. For now, have a nice day, and bye bye.